The idea of this paper is very interesting because instead of adding noise to all nodes, we add nodes to a particular subset of nodes. And also they have some super nodes that, because there are some blocks in chemistry, there are some blocks that is repeated. So they put all of them into one node, so your graph is reduced, so your training and sampling is more efficient. So these two are the major contributions of this paper in 2025. DMol, a schedule-driven diffusion model for highly efficient and versatile molecule generation. So they say here that unlike classical junction tree, it's very similar to that famous paper junction tree method for graph generation in MIT. Unlike that it involves VAEs and require complicated reconstruction steps, compressed DMol, their method, directly performs graph diffusion on a graph that compresses only a carefully selected set of frequent carbon rings into supernodes, which results in straightforward sample generation. So this compressed DMol method offers additional validity improvement over generic DMol of roughly 2%, increases the novelty of the method. Because graph size is reduced, so you have also improvement in the running time. So I say there are two major innovations in this paper. First, instead of perturbing all nodes, we only perturb a subset. So the first one is that. So it means fewer steps are needed. The second one is whenever you have a new ring, it is compressed DMol because you put it in a supernode, so your graph is reduced. This is similar to motif-based methods like junction tree variation autoencoder, but very simpler. Because why simpler? Because they only compress a small number of frequent ring types that are single bonded. The state-of-the-art graph diffusion methods for generating small molecules like digress, of course, this model is on top of digress. The training is very similar. Relies on a cosine noise injection mechanism that controls the amount of perturbation during the different diffusion steps. So every node and edge in the graph is allowed to be modified at each step. Unfortunately, its running time is expensive, and almost all samples generated in a run have unacceptably low biomedical scores, seldom tested in the literature. So that's why this DMol directly relates the diffusion time steps with the number of nodes and edges that are allowed to undergo state changes in that step. So it allows to have increased learning rate. And DMol can operate on graphs which compress important motifs into supernodes. And the key idea is to combine diffusion models with compressed motif representations of molecules, same as the one in junction tree variation autoencoder. This paper, I think, is from MIT. So let's review the graph diffusion, particularly that digress method. So we need a transition kernel, and because it's a Markov, so it's a combination of that, you can reach till time t. You don't need to do it every time step. You can, if you just use q bar instead of q, you reach at any time that you want in this time span. So you don't need to gradually go there. So that's why you multiply all of the transitions. But the DMol idea is that diffusion relies on randomly selecting n nodes and m edges at each time step and diffusing their labels to generate a noisy graph. So here we select only n nodes and m edges. So the difference is here that we randomly select n nodes. This is the forward process. We randomly select u nodes and v edges instead of all edges and all nodes from the subgraph induced by the u nodes and generate filter matrices k sub x and k sub e. I mean, for nodes x, for edges e. So it's just an indicator of the selection. So we replace kxx and kxx tilde. So we replace this with kx tilde. Similarly for edges. Because it's an indicator function, this k, so it is selecting a subset of edges and subset of nodes. That's why we represent them like this. So we just replace it with here. Okay. So to start the sampling process, we need to compute the marginal distribution of nodes and edges at time t. After sampling the random graph, we use the denoising model to predict the clean graph and continue this process iteratively. So the loss is just like the digress that they use cross-entropy for nodes, cross-entropy for edges, but they have two more things. As I said, then you have only select n nodes and m edges. So mean square error of d of argmax and n. So the DMol diffusion model is permutation equivariance. This is the proposition here. The second proposition says that DMol loss is permutation invariant. And we arrive at a similar conclusion for the mean squared error in terms of this, that invariance follows based on the definition of D. Okay, so just like this paper in 2019, as I said, this MIT paper, we incorporated into DMol a ring compression process. So you see in figure 3 that it's just a ring compression. You know, instead of all these complicated nodes and edges, you just put just one node, one super node. So your model, your graph is reduced. So it's easy. So let's review this transition matrix for nodes and transition kernel for edges. So let's review what it means when we write this. So K, first of all, is a number of classes. Beta is the noise at step T. So if beta T is 0, it means that it only is identity. Otherwise, it's not an identity. So it's noise schedule. Most of the algorithm, we fix it. But some papers recently, they learn it as well. But because its sampling is not differentiable, so they use Gumbel softmax. And this is the categorical variable with K class. So your Q matrix is like this. You know, if you look at the diagonal, you see the probability of staying the same class. For example, if your class is carbon, you stay carbon forever for this the next at time t. If oxygen, you remain oxygen. But the off diagonal is the marginal is uniform distribution, 1k, 1k. So it's uniform distribution. So 1 over k if you multiply by, because 1k is just a column vector of all ones, 1, 1, 1, and then multiply by the transpose of that. So it becomes 1, 1, 1, 1. So if it is n by 1, and this is 1 by n, so we understand it becomes n by n, so it becomes a matrix, so it becomes this matrix. You know the diagonal, you know the off-diagonal. Another way to write it is like this. Now, U notation, U here is just the one, that uniform distribution that I mentioned. There are different ways to write it. This is very simple, because you see, if it is diagonal, then 1 minus t, 1 minus, of course, this should be like this, 1 minus m of t, 1 minus m of t, in the diagonal 1 minus m of t, and the off diagonal is m of t over k minus 1, m of t over k minus 1. So it becomes this. So in DMol, the number of nodes ongoing state change at time t equals n of t 1 minus alpha n. So at the same time step in digress, the expected number of nodes undergoing state changes equals this summation over, because you have a marginal probability of node class I here, then we have 1 minus alpha times 1 minus pi x. So at the same time step, the number of nodes modified by DMol is 1 over that, times the expected from the digress. So they did experiments on, for example, Moses data set. They compare, for example, when we say like this, it means lower is better. This Freche distance, in images we say Freche inception distance. For graph we say FCD. Scaffolding, higher is better. So you see comparison, even they compare with the LSTM, they compare with digress. So their method is improvement. In FCD, higher is better. So molecule graphs you see on QM9 data set, their samples from their training looks like this.